Our week about transformers. And today, really the idea is just to go through the architecture of the transformer, describe all the parts, make sure that you have a good understanding of what it is. And then the next time we'll talk about, we'll get into iterations on transformers and how they're being used in a variety of things, not just what they were originally created for, which was for neural machine translation, but for a whole host of things, including computer vision and even very recent things, that are like something in between transformers and resonance. All right, so you remember last time we met, we kind of went through this whole thing about how to do neural machine translation using recurrent neural networks. And you remember that we went through how you would solve some of these more difficult problems and get state-of-the-art BLEU scores in a whole bunch of translation tasks. And in particular, for dealing with long sentences, learning the statistical interactions between words that are really far apart from each other in a sentence or in a document or something like that. This idea of an attention mechanism was introduced. Attention. And remember, it just looked like this. The idea was as you were learning the hidden state that you're going to input to the next stage of the decoder in your seek-to-seek model, your sequence-to-sequence model. What you did was you took the hidden state from the previous stage. You then used that and had some sort of way of scoring the similarity between this hidden state and the hidden states from the encoder, from each stage of the encoder. That gave you a set of coefficients. So we applied a softmax there, so we got a probability distribution. So that so the coefficients here, this is a vector of coefficients, one for each stage here. And then we used those as coefficients in a linear combination, meaning we took the first coefficient, multiplied it by this vector, the second multiplied by this vector, and so forth. Added those all together, and that gave us this context vector that then became the hidden state, the input to the hidden input to the next stage of your decoder. And in this way, instead of just depending on this aggregation, this forward aggregation of all this information here, this was allowing you to kind of at each time you need to decode, use that aggregated state, but then kind of go back and look at the states of the encoders and use those in some way, be able to kind of in a learned way, because these parameters here are learned, these attention parameters here are learned, in a learned way, be able to kind of recombine those and then that information so that you did a better job in decoding at that stage of the decoder. Sort of weird, right? Because it's the hidden state here is as I just said, it is an aggregation of all these. So in some sense, the thing here just is already contains all this information. And then you use it to kind of re-aggregate this information to go into the next state. So it's all there's this notion of self, you're attending to yourself in these funny ways. And so maybe before trying these things out, you would say, well, I don't expect that to work. All the information is already there. Why just reshuffling or re-weighting the input here help? But it does. It does in the context. Yeah, question.
Is AFT the same for each of the state? Does AFT stay the same?
You mean as you keep going decoding at each stage? No, because you're recomputing each time, right? So if we were to do the next stage here, I now have a new hidden state, and then I go and I take that and score that against each one of these, these hidden states here. Usually, when I'm saying score here, score similarity or something, usually this is like a dot product or something very, very similar to a dot product. So, that dot product is like a measure of similarity between vectors. And so you'd be computing, like, say that, just think of it in your mind as a dot product. At each stage, whatever the current hidden state is, doing that dot product. So that gives you like the raw attention scores. You pass them through a softmax, and then they become a probability distribution. And so what that means is you're doing a convex combination, this convex linear combination of these vectors here to give you this context, and that becomes the hidden state to the next stage. So it's not the same, it's different at every stage, because the hidden state coming out of here is going to be different from the hidden state that's coming out of the next stage.
So the weights, are they the same?
The
weights, when you multiply the hidden states times the weights, and then that gives you AFT? So,
there's no weights. There's no weights. It's literally this vector dot this vector. No weights. This vector dot this vector, this vector dot this vector, and so forth. You could have something learned there for doing the similarity, but in its simplest form, it's just like a dot product. Okay. All right. Cool. All right. So like that's your basic attention mechanism, and that, remember, allows you to have high blue scores. Remember this way of evaluating how good our translation between two languages was, for very long sentences. That's what the solid line is here, compared to other models not using attention mechanisms, which tend to have worse blue scores as the sentences get long. Okay? That matrix on the side there is just some representation of how each token tends to the other tokens.
Professor.
Yeah.
I'm sorry, but would you mind going back to the previous slide and go through the math again? So, for example, on that first red hidden state over there, you're gonna do dot product with the previous four.
Yeah, dot product here. That would give you
80.
That would give you one of the raw scores going into here. Like this is a vector of length 4.
Yeah.
Yeah, and then you do that each time, so that gives you 4 entries in your vector. Then you pass that through a softmax so that you get positive coefficients that sum to 1, and then you would use those as coefficients in the linear combination, right? So it's like the first coefficient, like that normalized coefficient times this vector, second times this vector, third times this vector, fourth times this vector, right? Then add those all together, and that gives you the context.
Okay, and the context
then becomes the hidden state that goes into the next stage of the decode.
Okay, so in this case, CT and HT are the same.
No, actually. Oh, I see what you're saying. Yes, yeah, it is. Well, let's see. Hold on. No, it's not, because this is the hidden state that goes into here, right? And then the way you get to the next hidden state is to, this is like your input. So there's a matrix times this, times this vector here. There's a matrix times this vector here. They get added together, like in the kind of a plain vanilla sense. Like this LSTM is more complicated, but plain vanilla, those get added together. You pass through some kind of nonlinearity, like a tangent or something like that, and then that becomes the hidden state.
Oh, I see.
So it's input into that hidden state.
Okay.
So it used to be, remember before that, it used to be this was the hidden state that went into computing the next hidden state. But instead, we used that to compute this other, hidden state, this other context vector that became the input to there. Yeah.
That makes sense. Thank you.
Yeah, thanks for asking the question. Other questions? Okay. So, yeah, I should have come over here to answer your question. This is actually, this is a little more, this has some numbers on it made up, but instead of there being 4 states, there's 3. So this is your decoder state at some stage in the decoding. You have that's your hidden state. You compute these scores, which is something like a dot product. You get this. You pass through softmax. You multiply those coefficients times those vectors. This has become grayed out because these are very small coefficients, right? So like this isn't contributing very much to the final output while this is, and then that becomes the context vector that goes into the next step. So like that's just like the math all over again in that step.
What do you mean by vector? Is that the decoder state, or multiply each vector by its softmax scale?
Yeah.
Oh, it's the H1.
This right here.
Okay.
What's this times this gives you that. This times this gives you that. This times this gives you that. Add them all together. That's that convex combination, and you get that. Yeah.
Yeah. So this context vector is used to feed the next time step, or
Yep. That's exactly right.
So at this time step we don't do anything with it. Then what is the point of keeping that context vector for this time?
Well, it's the context that goes into the next stage. Like, so it used to be that we passed in just the raw, like single kind of forward aggregated state, but now we're passing in a thing that instead of passing that in directly, we use it to calculate. It would have been that we would have passed that thing in as like the previous hidden state, but we do this thing where we sort of use it to recalculate things and get a new one, and that becomes now the hidden state for decoding the next token.
So that means we have to save every single hidden state?
For the encoder, yeah. Yep, that's right. Whereas before you wouldn't have had to have done that.
How does this even, like, it almost seems like this shouldn't work. It's
Why? I kind of agree with you, but I want to know why. I mean, I already said why, like in some sense, but go ahead.
It's almost like you're trying to weigh the past states, and then you're trying to say, okay, this is the state we should be focusing on. So it's like letting you almost like propagate something.
Yeah.
It's almost like the LTSM or the ResNet where you have a shortcut.
Yeah, I mean, it's not really a shortcut. It's just like it's this thing where instead of this, when this network learns everything end to end, instead of this thing being the vector that like has all of your all the information about what's happened previously, it's now this thing, which was computed by taking what used to be that thing, creating this vector, doing these dot products and setting them up. So it adds one little adjustment. So it could be that this we get the same vector out of there again if all the encoder all the encoder hidden states are in certain look a certain way or whatever. That could be the case, but in general you're gonna get something different. And the whole reason why it is better is that you're allowing yourself at each token to go back into the old information and just reweight it and put it back together. So I agree that it's weird because it's just it's like you just keep reusing all the same information over and over again. It's known as self-attention, and it seems odd that it should work. In my mind, it does seem odd it should work because all the same information is being used, but it does work. And we'll, as we get into transformers, we'll see that basically it's this operation alone that you do a whole bunch of, and once you do that, you actually have a very, very, very powerful encoder decoder system.
So how did people come up with this in the first place?
Oh, should we call up Joshua and see what he thought? Or the students who did it? I mean, if you think about it, it's pretty natural, right? It's okay, I'm solving the problem of very long sentences. I have this aggregated vector. The trouble with that aggregated vector is it saw the information from token 1 a long time ago. So it's likely kind of forgotten that state. So why don't I just do something that allows me to kind of go back and get it if needed. And you do the empirical studies and voila, things are better. Probably after a good amount of hyperparameter search, but still, voila, things are better, and then you publish a paper and you become famous. That's that easy. Okay, cool. So a paper in 2017 came out called "Attention is All You Need," and now everything is called "Something is All You Need" when a new breakthrough comes through in neural networks. But attention is all you need, and these this architecture became known as the transformer. And let me say there's lots of transformers now, but this is like the original. And all the components that you will see in other transformers are basically here. There's obviously differences, otherwise you wouldn't call them something different. But like in general, if you know this, you'll be able to kind of think about what the rest of the transformers are doing. There's a lot to it. There's a lot to it. And we're going to go through this today. We'll go through all these pieces. What you'll see here in just this schematic, this really famous schematic that you'll see all the time if you're reading about transformers, is that there are these blocks here where you'll see multi-head attention, and each one of these blocks is where all this attention is all you need. It's where all this attention is happening. So the thing that we just saw is basically just done over and over and over again, and just processed forward in the encoder n times. N's 6 typically, or was in this paper. It's again hyperparameters, but you kind of do this encoding 6 times, and then you have encoding, a final encoding, and that then becomes input to contextual input to the decoder, which does a bunch of this attention conditioned on the encoding. Do that 6 times or n times or whatever it is, and then like we had before, you have some layer that takes you from those encodings of the tokens and transforms those into probabilities over your vocabulary, and then you're making a prediction about which token goes where in this sentence. Okay, so we'll get into all this here in a second, but here you go. Oh yeah, this is done in this is done in this was originally done for things like neural machine translation, where you would have inputs in one language and outputs in a different language, or you could just have it predict the next. Just focus on learning just a single language, and you would have the outputs be the inputs, but shifted right. That's why that's the shifted right. The shifting right is what makes this autoregressive, right? You're going to predict the next token. We'll get into that. Okay, so this is what a transformer is. First of all, just raise your hands. Is there anybody out there who's in this class because they kind of just like deep learning, but they've already been doing a bunch of transformers? Anybody who's seen this, work with this before? Okay, cool. So we're all brand new here. Fine. Okay, so first of all, the results. So, remember our blue score? We have an English to German translation task and an English to French translation task. It's the same task that we've seen a bunch of times. They're doing it now in 2017 with these transformers, and they get state-of-the-art blue scores. Importantly, these blue scores come at far less cost. So it's actually, you see that this is the base model, then a bigger transformer. The bigger transformer, obviously, bigger is better, right? So we got better blue scores, but you can see that the number of flops during training, each training pass, is something on the order of 10 to the 19. And you can see for most of these models, you can see this is 10 to the 21, 10 to the 20. You see some 10 to the 19s as well. 10 to 18%, it doesn't perform very well. S2S is the sequence to sequence, so something the thing that we've been looking at. But you can see that we get state-of-the-art blue scores here. So this was a big deal, some a totally different kind of architecture, and also in state-of-the-art scores. So, what drives all of this thing? So, again, at the core of this is all these multi-head attention modules in here, and those look like the following. You have this thing called the scaled dot product attention. That's basically what we were just talking about. It's taking dot products to do comparisons. What kind of things are you doing comparisons of? Well, we'll see there are things, you'll see these variables v, k, and q, value, key, and query, and we'll look at in more depth there. And for each one of those, there's like what you can, it's called multi-head attention. There's actually like many different attentions being learned in parallel, and each one of them looks very simply like this. You have, we haven't said how this happened, but you get sort of three matrices. One's containing values, one containing keys, one containing queries. You do comparisons between the keys and the queries. This is the reason for the language is to compare it to document retrieval, where you have like keys for stored documents. You have queries that then go in and try to retrieve things similar to those keys. So you get this comparisons, like these dot products. There's a scaling we'll talk about. There's a potential masking to add like an autoregressive portion of this, which again we'll talk about. Doing some normalization, and then what you get out of this is then using these coefficients to give you linear combinations on the vectors in this matrix V, the values. So there's a very this is attention just like we looked at, but done in many different layers, and at each layer, in each module, done many different times in parallel. Okay. But in the end, don't forget that this is very much like what we've been looking at for recurrent neural networks. We are going to input, something like our, in this case we flopped it around, now we're starting with French as our input, but this is basically learning to encode each of these tokens here, and it's not actually these tokens. We'll talk about the embeddings, but those get passed through many, many layers of encoding, and then those then go through many, many layers of decoding. At the end of that, you get something that looks like the translated sentence, "I am a student." So even though there's lots of arrows and colorful boxes and things like that, in the end, all we really have here are many layers of encodings, many layers of decodings, with the objective of turning something like this sentence in French into the corresponding sentence in English. Okay. Yeah.
Looks to me that the decoder over there takes two inputs, right? The previous hidden state and also the output from the encoder as well.
Yeah. So you can see here each one of those so each one of these encoder modules is one of these things here, and each one of those decoder modules is one of these things here. And what you can see is exactly that, right? That there is input to each decoder layer coming from either the previous layer or the supervised tokens here, and then that's also conditioned in this. So there's two. So where there's only one head here. We'll see this in the next slide. But there's only one multi-head attention here in the encoder layer. There's two here. One that deals with just the incoming input, just like this. But the other one that is conditioned on the encodings from the final layer of the encoder. So where there were there's keys, queries, and values here, all coming from just the input. There's keys and queries here coming from the encoder, and then values coming from the output of this head here. It's kind of complicated in some sense because there's just a lot of arrows and things you have to track, but pretty simple once you understand kind of one of these multi-head attention modules, which is where we're going with it. I've basically just been saying this, answering your question. Encoders look like that, decoders look like that. One thing to note here is that each token, from our input, it is going to represent, a token that's going to be basically we're going to have for every token in the input, there's going to be one token in the output, all the way through all these layers. So there's a one-to-one correspondence between the number of encodings that we have and the number of input tokens that we have. And like at every stage of this, that's what we're going to see. So like this gets like transformed into this, gets transformed again here, and that becomes input in the next one, and so forth. So like if there are 3 input tokens, there's going to be like 3 encodings all the way through, and then there'll be 3 tokens that come out as conditioning into the decoder, but we'll decode to however many tokens we need in the output. So that's an important thing to just note, just kind of like remember that as we go through this, so you don't lose track of that. And yeah, that's like basically the same thing. So let's just start going through this. We'll go through like what the multi-head attention is all about. Right. So, by the way, I took a lot of these graphics from a really excellent blog post written, around the time when these came out. The citations down here to go look at it, but it's called the Illustrated Transformer, and I totally encourage you to go look at that after this if you haven't looked at it already, because it's a really, really nice walkthrough of all these ideas, and you'll recognize these graphics. Just really well done. So, what does this thing about self-attention, meanings, queries, keys, and values? So what's going to happen is at every time we come into one of these modules, we're going to have something that represents each token. I mean, if this is the first encoding layer is going to be, there's some way of creating those embeddings. Again, we'll talk about that in a second. But if we're multiple layers through, then there's some learned transformation of that token that now becomes input into the next module, the next attention module. And each one of those modules, for each of what's called a head, an attention head, there are going to be 3 parameter matrices that we're going to learn. One corresponding to Q, the queries, one corresponding to K, the keys, and one corresponding to V, the values. But the way that we get these queries, keys, and values is nothing more than multiplying, this matrix times this vector. So remember, this feeling we had about wow, this is all weird. It's all the same information. We're just kind of reweighting it. This is definitely happening here again, where we create the things that we're calling queries and the things that we're calling keys and the things that we're calling values as simple linear transformations of the current encodings for our tokens. Again, it's literally just a vector times, a matrix times a vector. Here, because these are all rows, this would be a vector times a matrix, but whatever.
How do you obtain that embedding?
Yeah, that's yeah. Well, that's the thing I said. We'll talk about it in just a second. But at the input, there's a way of creating the embedding for the input, and then this is just this would just be the output from the previous encoding layer. Just vectors from the encoding. But we're not seeing out the whole picture yet. Just kind of stick with me here for a minute, and if we don't answer that question in 20 minutes, then ask it again. But here's what we're learning. We're learning these matrices that transform whatever our encoding or embedding is of these tokens at this level, how we turn them into queries, keys, and values. Okay, so there's a lot of shared information there because again, you're just multiplying different matrices by times the same vectors. Okay, and we're going to do this for as many attention heads as we have per module. And this is a hyperparameter of these things. In the history of these things, it turns out that when this group was first working with what became known as transformers, they only had one of these heads per module, but they found it to be very, very unstable in terms of training, and they found that they had many heads that they would get much better performance per module. So for each one of these heads, H might be, 4 or something like that. There's going to be, a different set of these 3 matrices, these parameter matrices to learn. Okay, so each one has a different set of parameters, and that's what makes them different. So this looks a little bit like, how convolution happened, where we're learning many different filters, like, at each layer. This is like we're learning many different query key value matrices for each head in the attention module.
Where does query key and value come from? This?
Yeah, this is literally our input times this matrix gives you this.
Oh, okay.
Yep, input times this matrix gives you this.
And then input times Q of K gives you key?
Yep, exactly. X times WK gives you K, X times WV gives you V. And then we're just noting that there could be many of these heads, and so we have many triples like this for each, one triple for each head. Yep, so again, like this is the self part of this, they're all just linear transformations of our input, which is like the thing that I was just saying earlier, that's like strange that this works, because it's all just the same information, but it seems to work really well. And again, here's now like that whole operation of how we get to the the transformed output. So how does this work? There's this equation up here. Once you have computed this Q, the Q, and the K, and the V. So these aren't the weight matrices. Remember, these are the output of multiplying the input times the weight matrices, Q, K, and V. Once we've done that, we're going to, just depending on the dimensionality, we're going to have, this vector Q, or this matrix Q would be like 2 by 3, so 2 rows, 2 queries, each of like 3. Same thing for the keys, same thing for values. So once we've done all that, then how do we get the output from this attention head? We do exactly what we've been saying. We derive the Q, the K, and the V from our input x1, again, times those parameter matrices. We take a dot product with them. We might get something like 112. Again, these are made up numbers just to make things simple. So there's our, there's this like comparison. This is saying something like, in document retrieval, it's like, there's a document associated with like key K1, and we come up with a query that's like, represents some other document. We want to know how similar these documents are, so we do this dot product. That's kind of like, just to kind of hang some thought about why we call this query and key. So just a comparison there. It says this gives us some notion of like how similar they are. It's not, because these are not like normalized. It's there's some kind of scale. There's some kind of like inability to compare these things because they might be on different scales. But what we do is we do scale everything by the square root of the length of our vectors, which should be 64 if you're going to divide by 8, but we don't want to show 64 squares, so we're just showing 3. So again, all for illustrations. But you're going to divide by something that's the square root of the length here. So once you do that, you get other numbers, right? So these are now scaled numbers. We just took these, divided it by this thing. Why it's like this is again one of these things like it works kind of idea. The idea of like why the square root of dimension that has to do with things that like when sampling, like this is a natural kind of expectation for the variance of like unit normals of this size, this dimension. It's like central limit theorem kind of things. Anyways, all you gotta know is that it works. So you get now these scaled dot products. Okay. Once we do that, we want to turn these into a probability distribution, so we apply softmax. Now that's going to give us coefficients for how we're going to combine all of the value vectors. So remember before when we looked at the original attention, what we did there was we would have just used these keys again to retrieve these things, like to give you the value. Like this, we didn't have a separate learned value that we combined together. We just would have computed these coefficients and then applied them to these keys. But here we've allowed ourselves to learn another set of values. Again, just another set of vectors. We combine them with the coefficients that we've got out of using the queries and key vectors. So we take these coefficients, multiply the value vectors here, combine them, and then that becomes the output from this attention head for that token. And then the same thing would happen. So within the same attention head for the other token, instead of just right. So the way this would change is that these would be Q2s instead of Q1s. Only thing that would change there.
So there's no optional mask?
Yeah, not yet. This is on the decoder side.
Yeah, would you mind go back to the previous slide?
Sure.
Yeah,
Or I don't mind.
I'm still not sure what is the depth H right there. So
What is the what?
how do you combine that?
Yeah, so we haven't gotten that far yet. So what we've done is we've looked at this right here. We've looked at basically one head, so one of the H heads. Okay. And we've transformed our input for each token into an output for each token. Okay. Self-attention. All we have are learned parameter matrices that linearly transform our input matrices into these query, key, and value vectors. And then we use all those in this way to do this reweighting of the value vectors so that we get an output. So this is no one here should be like, oh wow, that's amazing. I totally understand how this works now. Because this is just like the operations for how it works. There's really very little intuition for why it should work. Just yet. We're setting up a system that allows itself to learn over many different kind of layers of operations like this to transform its input using information from the input. Okay, so we do this for one head. So again, this is an unrolling of all the operations that went into that equation up there, right? Softmax of Q times K's. So all those dot products, that's what that Q times the transpose of that gives you this nice outer product, scaled by the square root of this dimension, and then all that multiplied by B to give you the attention layer output.
So why is it Q1 times K2? Is that
because we're computing the output for just for the first token, but we do exactly the same thing for Z2. It's just that these would now be Q2 and Q2 here.
But how come K is allowed to look forward?
Sorry, say it again.
How come K is allowed to look forward? Is allowed to look at the next value of the sequence?
So in the encoding, there's no notion of there being looking ahead or looking backwards. You allow everything to look at everything in the encoding, right? You have the whole sentence. This is one of the important aspects of why this is this works better than an RNN, is that you don't enforce the autoregressive part of an RNN onto the encoding. You allow, so basically, even at the first level of encoding, all of the tokens mix together to possibly update themselves.
So you're sending the whole
here.
sentence as
The whole sentence goes in all together.
So you're not trying to translate as you're getting the sentence.
No, this will only apply when you do the decoding. In the decoding, this is what the masking is about. You have to enforce the autoregressive nature because you don't want there to be the ability to like decode from a word that you haven't yet like created in the translation. That makes sense? It's a great question. That's it's good perception on this. Did everybody get that point? The question was asked, why can I use information about the second token here, that's K2, in creating the encoding for the first token? When when we've been looking at recurrent neural networks up to this point, everything's been done sequentially. And the point is that there's no need when doing this translation task to learn the encoding sequentially. Right? You have the whole phrase, you might as well use the whole thing. Like when I'm giving a human the task, I give you the whole sentence. I don't give you one word after another and say decode it. I say here's the whole sentence, now decode it. Or translate it, I should say. And so that's what's happening here. So it's a different inductive bias entirely. Importantly, it allows, in the first layer of encoding, it allows all of the tokens to influence each other immediately. And so in that way, this looks a lot more like a fully connected layer than convolutions, obviously, because convolutions are fully connected, and then in the RNN inductive bias. So it's a very, very general inductive bias. This is one of the things that people love about transformers in the theoretical community, is that this is very much very, very few assumptions are being made about what the data ought to look like.
I don't know if you've already brought this up, but it's just something I'm thinking about, as you're talking. So every time we're moving on to getting the new word and our translated sentence.
So we haven't got there yet. This is all encoders. So when we get to decoders, we're going to talk about how things should change to get the next word in the sentence. And it's literally just going to be when we do this stuff over here, we can't use the tokens ahead in the sentence, or whatever the grammar is, whether it's forward or down or whatever. We can't use those to do the decoding. So we set those basically to 0. They have no influence, right? So the coefficient here on these things will be 0. That's this masking part. And that's what makes this autoregressive. The word autoregressive means that, we're moving forward, we're regressing forward. That's kind of fun, regressing forward, but we're regressing forward in the sequence only, conditioned only on what we've seen in the past. Question?
Yeah, so Z1 here is a function of V1, V2. But if a sentence has 40 words, then it's a function of V1 to V40.
Exactly.
Okay.
Yep, exactly.
Yeah, I thought it was the two near.
No, it's great. That's a great point. Thanks for pointing it out. Yeah, if this, this is all just done for very simple illustration, but of course it could be very long, and you can see now why this might do way better on very long sentences, and that is in the very first, in the very first layer, in the very first attention module, all of the tokens can mix together and influence each other, and you can't do this in the encoding of using an RNN. That's not how that model works. You try to kind of reproduce that with attention on the decoding side, but you've already learned all the encodings. This is at that point you've already learned all the encodings. You're just reweighting at that point. Here, you're literally just learning the encodings by letting all the tokens influence each other. So again, a very general inductive bias, meaning the family of things that can be learned here. And again, the analogy is this looks a lot more like a fully connected layer where all of the tokens can connect to each other and influence each other. These are great questions for understanding. Other questions? If you're feeling confused about this, that's totally valid too. We'll try to kind of come back to this over and over again and reinforce these ideas. But But this is it. Like this is really important. Like this is the crux of what a transformer is. This self-attention here. Mm-hmm.
So can you take this whole encoder layer and just stack multiple ones?
Yeah, that's what we do. We take these encoding layers and we just stack them one over another.
So you have multiple.
So like these, and this is not quite right yet because you'll see what we do a little bit. But just think of it as like these are now like the the green embeddings for the next layer. It's not quite right. You'll see in a second, but we allow one more linear transformation of it. But
so yeah, if we start stacking it this way, aren't we going to lose our gradients? So don't we have to make shortcuts?
You'll see that there are shortcuts. Yeah. That was is it in the original picture here? Yeah, you can see it here.
Oh, add norm.
So you have this right here, this added norms. This is a residual connection. So the input you add to the output of this, and then there's a normalization layer. We use layer norm, not batch norm, but very similar. And the same thing here. So we do have those tracks. So like everything after residual networks basically like learned its lesson and does these kinds of things. Good question. Okay, so like we were saying, like there, h might be 4, it might be 8. I mean, it's a hyperparameter. Here, there's 8. So we're going to get some transformation of our input x for each of the different heads. Again, the differences here is that we've learned a different WV, WQ, and WK for each one of these heads. So it changes what the queries and the keys and the values are in each head. Think of that, like the analogy here is like, again, a convolutional layer. You have multiple filters. Each one of those, is giving you like a different transformation of like the input, whether that was the original input or the activation layer or activation map from before. And you get these outputs. So what do you do with them? Well, it says right here, concatenate and then apply a linear transformation. So literally, you concatenate all those together. You have one more learned matrix. This WO for output here of the right size so that you get back to the original dimensions of your input. And there you go. Now you have your output, your final output Z from the multi-head attention. So you had all these heads, maybe like 8 different attention heads. They all produced some kind of output for the inputs. Concatenate them all together, multiply by some learned parameter matrix, and get now the output of the original size. You need that output of the original size because you're going to do a residual connection, so you need to be able to add these things together. Does that make sense? So like, we'll get to it in a second here, but yeah, there are additional
How
questions.
come Z has 2 rows?
Because there's 2 inputs. There are 2 tokens in the input.
Oh.
It still unclear to me. What are the heads? Maybe you already explained this slide.
The heads are these. That's a head. This whole operation's a head.
Oh, so Z1 is a head.
No, this is a head right here. All of these operations all together are a head that gives you a Z1 and a Z2 for the X1 and the X2 that you input, or the Z1 through Z40 for the X1 and the X40 that you input. So this is all these operations together, which is like shown right there, is a head. And there are however many, there are 8 of them, and for each of those, remember there is 3 learned matrices that take you from the input to your query vectors, your key vectors, and your value vectors. So a head is these matrices that allow you to produce K or Q, K, and V, and then you use those Q, K, and V to compute the Z's. Again, one for the Z's, one for each token, one for each head, and then concatenate all those multiply by a matrix to get you back to the original size of your input, which was in this case 2 by 4. I'm not going to answer any more questions on it because we got to keep going, and if you just spend some more time like just going through the slides or any of the trillions of things on the internet about this, you'll kind of get it. And I think if we kind of see more and more of this, just as we go, hopefully it'll help. But that's it. So like, like this module right here was just that triple of matrices, and then like one of these matrices here, and then all those operations that we just looked at. Cool. All right. So, yeah, here it is. Like just what we've been talking about, just kind of succinctly. Each one of these heads has these 3 matrices. We use those to transform the input into these matrices, which we used to compute this matrix, and then we can get those all together and use this final matrix to produce as an output of the same size as the input. So the size of WO depends on like what this dimension from the heads of the outputs, and then however many heads we have. So that dimension times the number of heads, that gives you that like in this case the number of rows. You do that multiplication, you get back the same size output. Cool. So once we have that, then we can pass this thing through. So like, what kinds of things are being learned by these heads? Here's like an illustration of that. Here's an illustration of 2 different heads. So if we look at those, this is actually looking at like further along in the 5th of 6 layers, but this is just something I pulled from that blog post. We're seeing 2 different heads here, like at that layer, like head 0 and then head 1. Head 0 in orange, head 1 in green. What it's trying to show you is it's trying to show you those like scaled dot products between the different tokens within those heads, between the keys and the queries within those heads. For our token it here. By the way, you see how all these tokens are in this kind of funny format where most of them have this like underscore at the end. Not all of them do, but a lot of them do. And sometimes it's just like for a word that we recognize, but for other ones, it's got these kind of like funny boundaries for breaking this up. Anybody know what this is? Anybody seen something like this before? This is what's known as byte pair encoding. Have you heard of BPE, byte pair encoding? So it's a way of taking, your characters and basically like combining them into common groupings of the characters. So it's an algorithm that you run just on your vocabulary. And it's called byte pair encoding because what you do literally is that you run through this one time, you take the most common pair of characters, and then you combine them together. That becomes like a character. And then you do it again with that, with those combined characters as one character. And then you get replace. Then you get the 2 most common character pairs and combine those together. And you keep doing that. This underscore is basically like it's like the space after so like you have these sentences. So it basically indicates the end of the word. So tire is not the end of the word here. You see tire as like a noun and tired as this verb, and so it's common to see this. It's more common to see this than say like tire underscore, which would be like the full word tire. Anyways, this is called byte pair encoding. It's a very common way of taking your vocabulary and turning it into basically in the end like a set of integers that represent the common terms in your vocabulary. So byte pair encoding. Anyways, the point is that you can see that there's two different heads, and they're computing the representation of this it underscore term here, and using different contexts entirely, right? So one of these heads, the orange one, is, you can see it's paying attention to what? So it's like the darker the color, the more attention it's paying to it. So it's paying attention to, like the beginning of the sentence, the animal. Why does that make sense? What does it refer to in this sentence? The animal. That's great. So like that, like intuitively that makes sense to us. And it has some other parts here where it's like slightly attending to some of the other words as this is like this, as this it is transitioning into doing something else. This other head for this it is actually paying attention to like a totally different part of this sentence. There's this like kind of weaker reference to street, but it's mostly paying attention to tired here. So this it refers to the animal. So this head basically is like saying, okay, like we know that like we're paying attention to this because that's like semantically that makes sense, even though it's not learning semantics, but like it's learning something like that from all the pairs or from all the examples it's seen. And it's also learned that like that same animal, like the thing that it's referring to, like the thing it is referring to, is also being like characterized by being tired, which is very cool. If you go look at lots of examples like this, like you'll very, very often be able to kind of just pick this out and look and see like, oh wow, that makes a lot of sense. Like what this thing is learning to, like how it's using other tokens to encode information around it. And that's the beauty of these things, is that it learns to do this kind of stuff really well over very, very long sentences. In fact, it's not uncommon for transformers to have input of length 1024, for instance, or even longer than that. Whereas for RNNs, you could barely do more than a couple dozen phrases of length, 20 or so, because it just it starts to break down the ability to connect tokens far away in the sentence. I mean, there are tricks for it, but in general, this just does it way, way, way better, and for far less flops. Right. So a couple of the details about transformers. So one is this is really sort of interesting. So remember what we've been saying. We've been saying that from the transformer allows in the very first encoding layer to basically mix up, I say mix up, but basically let all the tokens interact with each other no matter where they appear in the input phrase, in the input sentence, or the input document. Which means, and if you think about it, we're just doing a bunch of matrix multiplication, which means that order here doesn't matter. Order doesn't matter at all. And you might expect that some notion of having an ordering to the sentence should help in understanding the semantic content of the phrase, because otherwise it's just like this bag of words. And so again, one of these empirical kind of tests that seem to work is that you have some way of converting your token into a vector, and the typical way this is done is through this byte pair encoding. But you don't just input that directly into the first encoding layer. You add to it what's known as, and it's adding, which is super weird, but you add to it another vector that's known as a positional encoding. And the positional encoding is what it sounds like. It's a way of encoding which position in the input this thing is at. So there's a vector here that depends on the length of our embeddings here, our encodings. that is calculated to represent this is the first token, and then another one that this is the second, and this is the third. And then no matter what these are down here, you just add these things to here, giving you like the actual input to the encoder, which is super weird. This adding thing is just really weird, but it seems to work. For the mathematicians that are here, if we're adding something that's like, has some sequential information, like what space do we, what space are we in? I should say the math. Anybody who expects some signal processing space, like what space does that like feel like we're working in? Not the original positional space, but some other space that has to do with what?
Time.
Who's done like Fourier transforms, right? So this looks a little bit like we've moved ourselves into a space where we're in a Fourier space where we're like looking at frequencies, where frequencies might add to each other rather than like be multiplicative in the original positional space. But we didn't do anything to these settings to like be in there. Anyways, it's super weird. The way that these things work is like they're literally like the way that you compute these coefficients of these again depends on the length and depends on the position through like a kind of sinusoidal transform. Again, kind of giving the notion of something related to Fourier transforms, but anyways, it's just one of those things that like somebody tried and it works. So you do this, and then here's a little more detail what we've seen. So you have your byte encoding, byte pair encoding, add your positional vectors. That becomes your input to your first layer. You process through a self-attention module. You get out your encodings. Those encodings are of the same dimension as your input, so that you can add them together, right? So that's now your residual connection. And then you do a normalization, which is layer norm here. So instead of normalizing by for each channel, you're now normalizing for, let's see.
Instead of normalizing each batch.
Yeah, well, it's still over the batch, but instead of normalizing for each, computing a mean and standard deviation over for each channel in the batch, this is now over each. Shoot, I totally lost this. Look at something.
From my understanding,
It's not the other one is instance. Shoot, I'm not. I have to come back and tell you because I've totally forgotten this in this stupor thought here in front of you all. But anyways, it's something very similar, but not the same as batch normal. It'll come in a second. I'll tell you. Anyways, then so now you have this normalized output that now goes into just like a feed-forward network that changes the dimension. It's weird. It expands it, and then contracts it back to the original size. So you have these like couple of linear layers here. That's what this feed-forward is, linear layers, but it expands it and then contracts it. So that you can then again do the same, you have this residual connection, you add them together and normalize, and then that's the output that goes to the next encoding layer. Weird, huh? So the output from there now goes to, I don't know, why do I have this over here? This is just an expansion. Okay, so even though it's sort of weird and I wouldn't expect anybody here to be like, oh, I totally have a great intuition for why it's just like the crux of what a transformer is. Okay, 15 minutes. And now, we want to talk about the other side of this, the decoder. So the decoder is very much the same as the encoder. It's just that what we're going to be doing is conditioning there's going to be two self-attention heads here, and the second of these is going to like condition itself on the output from the encoder. That's how you get the information from the encoder and the decoder, and that's going to be our key and query. It's going to be the way that we get our keys and queries, but the values will be coming from the previous layers in the decoder layer. But the details are basically all the same everywhere else you look. You have these like self-attention, this multi-head self-attention with the residual connection, the normalization. Do it again, but just the keys and queries coming from the encoder. Then have the feed forward like we had before, like the fully connected layers expand and contract, and then you come out of that to the decoder. That's the output of the decoder. Go to the next decoder. And let's see. Right. So again, this is like another view of how all this goes together. But now we're looking at like what happens at decoding time. I don't know why I have this. It's funny. I went through all these slides again, like right before this. I think I know what I'm doing. So now what do we do in the decoder? Like how does this all work? Well, we during training we have for this neural translation task, the machine translation task. We have our phrase in French, and then we run through our many layers of encoding, and we get out this output. Again, one like representation of one vector for each of the original tokens. On the decoder side, while we're training, what we want to do is we want to learn the we want to learn to be able to decode to the sentence, but we want to do it in such a way that and we talked about this already, but where we don't want to be able to use any word that comes, like especially so for this kind of grammar, any word that comes ahead of the word that we're trying to decode. So everything kind of looks the same. You have this dependence on the encoder, as we talked about, but we don't want to be able to use think about it as like using the future to like understand the present, because like there's a kind of causal error that we don't want to interrupt. So the encoder or the decoder is almost like the encoder, except for the two different things, like the thing we just talked about. But what we do for these future positions in the self-attention is that we force the coefficient on the values to be zero. I already said this earlier. We force them to be zeros so that they do not contribute to the representation of that decoding of the token, the decoding token. Right? Because otherwise, like we said, they'd all be able to mix together. They'd all be able to mix together. But we don't want to be able to do that. So we enforce this kind of this autoregressive nature on this by saying like when we're trying to decode this decode this token, we can't use any of the tokens that come after it. And basically, like everything else, is the same. It's the same. Questions about that? Okay. So there are these results again. That I showed you at the beginning, so for translation. These kinds of things can be used to do all kinds of interesting, like NLP type tasks, natural language processing tasks. And what I'm showing you here is another result from the paper, from the original paper here, which is about parsing the sentences into their parts of speech and labeling those. And the point is that this is giving, again, state-of-the-art performance on the ability to parse. So the things to compare here is you see transformers, like these are 4-layer transformers. So this is some score on the ability to do that with far less flops, using a particular data set and fully supervised what this is. You get, this isn't like the best result here, but it's close to the best result. In the semi-supervised task, where again, using similar data sets, but only supervised by like parts, by some of the sentences having labels and other ones not, just learning like a basic embedding of those, you get state-of-the-art performance on those. And this is just the first paper, and so again, like in the next lecture, we're going to kind of dive more into this and see like where these things have gone since this first paper, how the transformers have maybe changed a little bit in terms of like dealing with some of the issues that the transformers have, like computation-wise, and like all the amazing things that they're being used to do, including like the cool things that you see, like with GPT-3, for instance, this ability to like generate with just a little bit of like introductory kind of starter text, be able to generate like very, very, very like believable, tokens like that look grammatical and that like seem to fit a certain pattern as introduced in the previous text. I think that's the thing. Yeah. So, questions about that? Questions about transformers up to this point? We have just a few minutes left, yeah.
So for the positional encoding, it's almost like a Fourier transform that you're summing together with the signal.
Yeah, I mean, like, it's as if you're in a Fourier space because you're able to like sum the position, but you didn't really do anything to like.
But that's like gonna make a whole bunch of other words like hot or something, or
it's like what?
It's gonna make because X is a vector of all the words in your vocabulary, though.
Right, like those haven't been like transformed in any way into like a frequency space, right? I don't know. You add it and it works. I think everybody kind of looks at this and goes, "Why should that work?" I don't know. It works. You do. And what's interesting is that like you could have learned those positional encodings as well. And in fact, if you do learn them, you get about the same performance as if you just add them. But if you don't learn them or add them, then you get worse performance because you're not giving the network this additional information that like these things are in this order.
So
these tokens are
is it just an unweighted sum between the two, between the position representing the?
Yeah, I mean, it's just you're literally just adding them together, like that fixed vector. I didn't show you how to compute it. You can look up in the paper, but there's that fixed vector that exists for position 1, and then position 2, and position 3. You just always add the same vector for that position to your byte pair encoded token. Works. That's all I can say. Other questions? All right. Well, happy to answer individual questions now after class. We'll see you on Thursday.